Okay, welcome back. In a previous video, we learned all about so-called non-deterministic finite automata. They are finite state machines with a certain degree of non-determinism built into them. And we talked about how they're more flexible because we can sort of easily, well, they're easier to write and to reason about in certain circumstances. They appear to have more expressive power, but what I claimed at the time was that they actually don't. And so here's an example of a non-deterministic finite automaton. It has three states, labeled 1, 2, and 3, and it is non-deterministic in all the sort of three ways I highlighted as being features of NFAs. One is that sometimes there are no rules at all for what to do. So for example, from state 1, if you read an A, there's just simply no direction of what to do. Also, crucially, part of the non-determinism is that you're allowed to have multiple transitions from a state on a particular character. So note that in state 2, if you read an A, you are simultaneously being told to stay in state 2, but also to go to state 3. And finally, there's this Lambda transition, so-called Lambda Transition. Other authors use epsilon for this, which sort of is like a free pass from state 1 to state 3. So in some sense, whenever you are in state 1, you should sort of also go to state 3. Okay, and this is, I think, quite complicated and difficult to trace. And given a particular input string, we saw in the previous video that we can create a kind of tree, and we can sort of think of the NFA as branching and making sort of copies of itself into a bunch of DFAs. And the big idea is if any of the DFAs, if any of the sort of copies lead to an accept state, then we should accept the string. Okay, well, what I'm now going to convince you, hopefully, is that with this greater expressive power, we do not actually gain any power. That is to say, every NFA is just shorthand for a DFA. And so we may feel free to sort of reason out at the level of NFAs. And this is the kind of standard thing you would do in a course on this, and Gossett just mentions this briefly but does not explain the algorithm. Okay, this is called the powerset construction, and it's actually totally intuitive. Here's what it says. It says, okay, here's the big idea. The big idea is that when I'm in state 1, say, and I read a B and I go to state 2, then I read an A. Well, one way to capture the intuitive notion that the machine has split into two machines, and one processing of the string remains in state 2, whereas one moves to state 3, is to just imagine that we are, in fact, in some kind of combo state 3 and state 2 and state 3 state. In other words, it's called the powerset construction because if we can be in sort of two places at once, or possibly even more than two places at once, then we should consider all possible combinations of places where we can be and imagine just that we're there. In other words, here's what we do. We say, given that this machine, this NFA, has three states, let's construct a DFA, a deterministic finite automaton, which contains a state for every subset of states in this NFA. Okay, and so I'm going to do, sort of right now, oh man, really wish I had a bigger whiteboard. Let me think a little bit more carefully about this. I guess I should make my states small or something like that. So, okay, let's do this. One, I want more space. 2, 3, 4. Okay. Okay. So what's here is the construction. So this is basically an algorithm to convert a NFA to a DFA. Let's go. First, 1, well, we just make a state for every subset of 1, 2, 3. So this is the empty set machine. This is state 1. This is state 2. This is state 3. This is just 1 and 2. This is 1 and 3. This is 2 and 3. And this is 1, 2, and 3. Okay, good. So now I can always sort of be in precisely one of these locations. Okay, and I can't remember what the sort of logical way to do this is. Let's see. I'll try to use some new colors now or something. Okay. I don't remember what to do. I guess it doesn't matter. Okay, so, well, okay. Let's just start at the beginning or something. Here I am in state 1. Well, the thing about being in state 1 is that you're never really in state 1. When you're in state 1, you're really in state 1 and 3. Okay, but there is something about being in, well, okay. So let's imagine that we are just in state 1. Though I claim that that can't actually possibly happen, I still am going to make this algorithmic, and so you don't have to be kind of smart and understand things to be able to follow it. That's the whole idea of an algorithm. So imagine that I am somehow only in state 1. Well, if I'm only in state 1, then I have two options, right? I have the option of reading an A or reading a B. And what happens if I read a B? Well, that's, I think, pretty uncontroversial. If I'm in state 1 and I read a B, I'm supposed to go to state 2. So I add a transition which says, if you read a B, go to state 2. And what if you read an A? Well, notice in the NFA, I don't worry about that. I just simply have no arrow leading out of state 1 labeled with an A. So that is to be interpreted as, if you're in state 1 and you read an A, you just die. Well, that's kind of what the empty set state is, right? The empty set is just some kind of state where it's a kind of a garbage, it's what I think I referred to in a previous video as a garbage state. It's a state you just go to full of when you just, your string is going to die. And so when there is no direction for what to do on a particular input, you can think of that as being shorthand for go to some new garbage dead state where you go there and you just never leave. So that's how we capture this sort of die idea, is go to this empty set state, and once you're in the empty set state, regardless of whatever characters you read, you don't ever leave it. Okay, good. What's next? Well, let's go to state 2. If you're in state 2, and you read an A, okay, well this gets kind of complicated, because if you're in state 2 and you read an A, you're supposed to both stay in state 2 and also go to state 3. Well, that's easily solved by simply going to state 2, 3. This state, labeled with the subset 2, 3, is the state which captures the idea that I'm in 2 and 3. If I read an A, and if I read a B from state 2, I should just go to state 3. Okay, so there I am. Great. What if I am in state 3? I'm just kind of following along in some kind of depth first type way, I guess, or something. If I'm in breadth first, I don't know what I'm doing. If I'm in state 3 and I read an A, I'm supposed to go to state 1. Okay, but here is our first kind of a thing. Because look, if I read an A and I'm in state 3, I go to state 1. But as soon as I go to state 1, this lambda transition sends me also to state 3. And so from state 3, I sort of automatically go to state 1, but I never just stay in state 1. I lambda transition immediately back to 3 again. And so the best way to think about this is that if I am in state 3 and I read an A, I should go to state 1, 3. Because that's sort of well, that's what we do. If you're in state 3 and you read an A, you go to 1, but also to 3. Okay, good. What about if I'm in state 3 and I read a B? Well, there's no rule for that, and since there's no rule for that, I transition away to my garbage state. That's what I do if I read a B. Okay, half done. What if I am in state 2, 3? Well, if I'm in basically 2 and 3, okay, here's where it gets kind of complicated, and I read an A, what do I do? Well, if I'm in state 2 and 3, and I read an A, well, if I'm in state 2 and I read an A, I go to 2 and also 3. But if I'm in state 3 and I read an A, I go to 1 and also to 3. In other words, if I'm sort of in 2 and 3 at the same time and I read an A, I end up in all 3 states. And so, from state 2, 3, I transition with an A to state 1, 2, 3. What about if I'm in state 2, 3 and I read a B? Well, if I'm in state 2 and I read a B, I don't go anywhere, because if I'm in state 2 and I read a B, I go to 3. And if I'm in, 2 goes to 3. And if I'm in state 3 and I read a B, I don't go anywhere. So in fact, from state 2 combined with 3, if I read a B, I go just to state 3. And so this is B. Okay, let's see. Let's consider this one. What if I'm in state 1, 2, 3 and read an A? Well, if I'm in 1, 2, and 3 simultaneously, I think I know what's going to happen. If I'm in 1 and I read an A, okay, there's no rule for that. If I'm in 2 and I read an A, I go to A, but also to, I go to 2, but also to 3. And if I am in 3 and I read an A, I go to 1, but then I Lambda transition back to 3. So once again, from 2 and I read an A, I go to 3, I go to 2 and also to 3 and also to 1. And so if I'm in state 1, 2, 3 and I read an A, I should go back to state 1, 2, 3. If I'm in state 1, 2, 3 and I read a B, let's see. Well, if I'm in state 1 and I read a B, I go to 2. If I'm in 2 and I read a B, I go to 3. And if I'm in 3 and I read a B, I die. Therefore, if I'm in 1, 2, and 3, I should be going to 2 and 3. And indeed, that's exactly what we do. So that's B. Okay, almost good. Now what? A, B. Okay, 2 more to go. What if I'm in state 1 and 3? If I'm in state 1 and 3 and I read an A, well, there's no rule for what to do when you're in state 1 and you read an A, but there is a rule for what to do when you're in state 3 and you read an A, namely go to state 1, but also go to state 3. Therefore, if I read an A, I am supposed to go back to state 1, 3. And if I'm in state 1, 3 and I read a B, well, from 3 there's no rule for what to do when you read a B, but from state 1 if you read a B you're supposed to go to state 2. And therefore from state 1, 3 if I read a B I am supposed to go to state 2. Okay, finally if I am in state 1, 2, what do I do? Well, if I'm in 1 and 2 simultaneously and I read an A, if I'm in 1 and 2 simultaneously and I read an A, from 1 there's no direction for what to do when reading an A, but from state 2 when I read an A, I'm supposed to go to 2, 3. Okay, so from 1, 2, when I read an A, I'm supposed to go to 2, 3. Okay, so there's no way to avoid this, maybe. We're going to do the little, what's the way to do that? Like you draw a little cha. I think that's what sophisticated people do in this situation. So that's to indicate that, okay, that's crossing, but don't get worked up about that. I think there's a different symbol actually, but whatever. If I read an A and if I read a B, then what do I do if I'm in state 1 and 2? Well, I go to 2 if I'm in state 1, and from 2 if I read a B, I go to 3. So it's also to 2 and 3. So we get A, B. Okay, and so what I've now done is to indicate precisely what to do from every single subset of states upon a reading of A or B. And the only thing left to do is to figure out what is the start state and what are the accept states. And I think the algorithm should be clear. This NFA is supposed to accept if we land in state 1. And so each of these states, which include a 1, is designed to indicate the fact that I am in 1 and possibly other things as well. And so I need to make every state an except state that has a 1 in it. And so in fact half the states will be except states. And finally, what's the start state? This is, I think, important. Well, now the start state is state 1, you might say. But of course, this lambda transition enables us to go from state 1 freely to state 3, which is why I'm never really in state 1. And so the start state of this machine is the state 1, 3. Okay, this is my attempt to do this with board space. I don't know if I made the right decision or not. I need some more board space. What I would like to pursue, which of these spaces looks larger? I guess this one is. Okay, what I would like to pursue now is an alternative. The alternative is, for this particular case, not so simple, but as I was, not so different. As I was doing this, you may have thought to yourself, oh, and by the way, sorry, I forgot to, I skipped over the exciting part, which is that this is a DFA. And so I've sort of removed the non-determinism, and therefore demonstrated, which was the big idea, that the non-determinism was not fundamental in any kind of way. It was just a shorthand for something which was in fact deterministic. Okay, the last thing I will do very fast, I hope this is fast, oh yeah, is to present the alternative construction. The alternative construction says, look man, you don't really need to construct a state for every possible subset of states, because that grows quite quickly. If you have, say, 5 states in your NFA, then you have, 32 states in your DFA. And many of those are going to be useless. This particular NFA is very sort of tightly connected, but most, won't be or something like that. And so I will present this sort of alternative algorithm. The alternative algorithm says you just make the states like as you need them, man. And so we just begin with the start state. I'll do this in 5 minutes, really fast. In the start state, I'm in state 1, is the start state of the NFA, but of course 1 lambda transitions to 3, which is to say that there is a state 1, 3, and that is an except state, because every state which contains a 1 will be, but that's the start state of my machine. And now I'm going to just build the machine as I go. And okay, well, what do I do if I'm in 1, 3 and I read an A? I guess I can use my old work, right? If I'm 1, 3 and I have an A, I'm supposed to stay there. So I'll just do that. So here I am, staying in state 1, 3. And what if I read a B? What am I supposed to do? If I read a B, I'm supposed to go to state 2. So let me now make state 2 right next to it here or something. And that's what's supposed to happen if I read a B. Okay, well now, from state 2, what am I supposed to do? Well, if I read an A, I'm supposed to go to state 2, 3. So here is state 2, 3, cha-cha-cha-cha. And if, what did I say? If I read an A, I'm supposed to go there. So A. If I read a B from state 2, where am I supposed to go? I'm supposed to go to state 3. Okay, I'm using some previous work I did over here. So I'm going to put state 3 here. And from state 2, 3, I am supposed to go here if I read a B. Okay, again, the logic all still holds, so everything's good. And, okay, what else? Oh, what if I read an A from state 2, 3? What am I supposed to do? I'm supposed to go to state 1, 2, 3. So I'll put that over here. Here is state 1, 2, 3, cha-cha-cha-cha, and that will be an except state because it has a 1 in it. And what did I say? That's what I'm supposed to do from state 2, 3, so that's an A. And good. Now, what about state 1? Oh, I guess I could do this next. What about state 3? What happens in state 3 if I read an A? I'm supposed to go to state 1, 3. So I go here if I read an A. But if I read a B, what am I supposed to do from state 3? Well, notice that here there was no rule for what to do, so we really are supposed to die. Therefore, I kind of do need to create an empty set state, and from state 3, if I read a B, I'm supposed to go to that empty set state. In the empty set state, of course, I just stay there, and I think the only thing left is to deal with this 1, 2, 3. If I'm in 1, 2, 3, and I read an A, then I'm supposed to stay there. Yeah. And if I read a B, I am supposed to go to state 2, 3. Okay, and now the algorithm stops. Because I already know my start state. I already know that every state with a 1, 2, 3 is going to be an accept state, and so I'm sort of done. Okay, so the algorithm is fundamentally the same. This one just creates every single state first. You end up wasting a lot of time. In fact, the relationship between these two algorithms, the original algorithm and the modified algorithm, is that in the modified algorithm, I don't waste my time doing certain things which are totally silly. And you'll notice that the very first thing we did is to consider what happens when you are in state 1. But notice that, as we mentioned, you can't sort of ever be just in state 1. And so you can think of the modified algorithm as being the algorithm which you just eliminate or delete or something like that, states which are sort of stupid and don't really need to be there. In particular, state 1 doesn't need to be there because it's never a viable option. And you can see that by seeing that there is no path in the sort of directed graph of states to this state. There's no way to reach this. There are no arrows leading to this state. And that's because we start in simultaneously state 1 and 3, and just no path leads ever to state 1, because any time in the computations that we're in 1, we're sort of also in 3. And so I just never made that state because it was a waste of time. And let's see, what is the other state that never gets made? This one, this state 1, 2, also never gets made because, well, for the same reason, I guess, right? I can never be just in state 1 and not also in state 3. And you'll see once again that there are no arrows leading to this state because it never happens. And the other 6 remaining states are the same. So the modified algorithm is just the full algorithm with sort of pruned by taking out the states which we can never reach. But in practice, it's probably much faster to use the modified algorithm. And the thinking and the logic is exactly the same. Okay, so you can have as many as, that's an upper bound on the number of states you need in your DFA, is 2 to the power of the number of states in the NFA. But in practice, it might require far fewer. Okay, good. We now see that NFAs and DFAs are equally powerful in the sense that, well, every DFA just automatically is trivially an NFA, and any NFA can be converted into a DFA, which does the exact same thing. Which means when we want to show that deterministic finite, that's why people sometimes just say finite automata, and they don't distinguish between DFAs and NFAs because it doesn't really matter. Yet we will often use NFAs, and just knowing that there is an algorithm to convert it to a DFA means we don't actually have to do it. We can just say, you do it if you want to, and that's it. Okay, good. This was the last video for the week, except I'm also going to make a video going over the homework from 9.2 and 9.3, hopefully somehow. Goodbye.